to say that it's a lower bound, but I'm asking for exact solution. Anyway, why is it not exactly equal? Exactly. So as she said and he said, it will not take care of cycles. In this case, his answer will be 0. And as he correctly pointed out, the number of nodes with integrity 0 will be a lower bound of the answer. So what is exactly the solution to this problem?
So you can do a topological sort and process from left to right.
This isn't even a DAG, so you can't do topological sort in this because this isn't a DAG.
Probably start with the vertex and do a DFS.
Okay.
So we mark all the visited.
Okay.
Okay, so that node, starting vertex, you put it in a vector int or something.
Okay.
The rest which is not visited, again pick one and again start DFS.
Okay, so for this graph, suppose I first pick this vertex, I do a DFS, I insert it into a vector int. So label it as 1, 2, 3, 4 and 5. So first I pick 5. You are surely telling 5 will be part of the answer, correct? But clearly 5 is not part of the answer. So anyone has a solution to this?
Instead of choosing a random variable to start with the starter DFS, you sort the nodes by the outgoing edge.
I sort the nodes by?
The number of
out degree. Okay.
And then you take the first node with that in the reverse order. So like in descending order. So now you take the first node which has the maximum out degree, perform a DFS from there.
Okay.
And then whichever one is not marked.
Suppose you have two sets, say, okay. The first set denoting the elements which are currently taken, and the second set will be complement of the first set obviously.
So, okay.
Okay. So from the selected set, you can choose any vertex.
Okay.
Okay. And we will try to cover how many vertices which are present on the second set.
What's the complexity?
Probably something 2 power
2 power n into, for each vertex you select n into a DFS m. Correct? Okay. So yeah, once again I'll explain the solution. He's telling a 2 power n into m solution. The solution is have a bit mask or a set of vertices which haven't been visited yet. So that is a part of the 2 power n. So suppose 1 0 1 1 0 is the bit mask now. That means 1 denotes that you have to visit the vertex. 0 denotes that you have already visited the vertex. What he is telling is, so I must surely choose one of these 3 nodes now. So choose each one of them, do a DFS. You know all the vertices which should be visited, and then call it recursively again. So 2 power n, the bit mask. There will be n choices at each stage, and each doing a DFS will be m. So the complexity is 2 power n into m. It is a correct solution, but we can do better.
So we started DFS from some random node.
Okay.
So and we maintain a list of the answer. We maintain the answer as a list.
Okay.
So we started DFS from one node and put it in the selected list and visit all the and do a DFS and mark everything visited.
Do a DFS and visit everything visited. Okay. So you're telling take a random node, insert it into a list, and do a DFS. Okay.
DFS. So I will take an unlisted vertex and start a DFS again.
Okay.
So in that, if I visit the node which I have selected already, so I will remove that from the list. So actually I will traverse all the edges only once. I will do a DFS from one node and I will start a DFS from unlisted vertex.
Okay.
If in that process I will visit a node which I have selected in the list, so I will remove that.
So what's the complexity?
So DFS. I will essentially visit.
You have to remove from the list and all now.
So I can just mark whether it has been selected in the list or not. So I can just. So essentially I will go through all the edges only once.
Yeah, probably it's right. But anyway, yeah, what he's telling is, take any random node, do a DFS from that node. Hey, I don't know. Check whether the solution is correct. Okay, he's telling. Pick for that question. Take any random node, do a DFS from that node. So, and the random node that you picked, insert it into a list. So the next time pick another random node and do a DFS from that node. But in this DFS, if you encounter this node which you have already picked, pop this from the list.
Push the current.
So I have visited this edge once.
Okay.
If I pick this random and I put this in my list.
Okay.
So this DFS on this may visit all these edges and it will reach.
The DFS on this has to reach this, it has to go through the visited.
So complexity, I don't know. Maybe it will work, but complexity
is high.
I mean, it's giving wrong answer here, right?
Yeah, it's giving wrong answer.
Not only complexity, it's giving wrong answer here. Yeah, so his approach is wrong, but he himself found it. See, from this node, you do a DFS. So you push this into the list. See, okay, my graph is this. And from this to this, yeah. From this node, I basically insert this into the list and all these three will be marked. From here we'll go, this will be marked, so I will try. Otherwise it will be exponential if you
do all the DFS.
Yeah, so for anyone interested, and a case where his fails is for this graph, let him initially pick this node and do a DFS. So all these three will be marked and he will insert this into the list. So the list will have this element. When he starts from here, from this he'll go here, but since this is listed and this is not in the list, he'll stop.
Okay, so first of all, start DFS from every node with integrity 0, and so you cover a lot of vertices, remove all of it. At the end, I'm clearing that it will probably be left into many Desjardins cycles, the graph, and the number of rows plus the number of nodes with integrity 0. Because there will be no node with integrity 0 at the end of your DFSs, so it will only be like lots of SCCs or something. So the number of such SCCs.
Again, take all the nodes of integrity 0.
Yeah, do DFSs and see which are vertices you can reach, remove all of them.
Do DFS. Okay, see which are vertices you can see, okay. Remove all of them, okay.
At the end of this, find the number of strongly connected components, this plus the number of nodes in the.
After the end, what do you do? Okay, take all the nodes of integrity 0, delete all them, then?
For each strongly connected component, just choose one. So this will cover all the remaining.
So then you will do a strongly connected components.
Yeah. So,
okay.
So number of strongly connected components at the end, plus number of nodes with integrity 0 in the beginning. I do DFS answer.
What is this? Wait. Example case. Wait. Get an example case for that. Number of nodes with integrity 0, you do a DFS, remove all the nodes which are reachable from them. Yeah, up till this it's correct because he proved that it's a lower bound. Yeah. Then after that, you're claiming it?
It's the number of strongly connected components left.
Number of strongly connected components left. Say, there are no nodes with integrity 0. Number of strongly connected components left is 2. But the answer is 1, any of these. Correct? It's wrong, right? Okay. So I'll first tell the solution for the sake of who knows strongly connected components. Solution is just number of nodes with integrity 0 in the strongly connected components. That is, first run strongly connected components. After strongly connected components, you will get a DAG. The number of nodes with integrity 0 in this DAG is the answer. Anyway, for the sake of everyone else, I'll tell. So, what is a strongly connected component? A strongly connected component is a maximal set of vertices C such that for every pair of vertices U and V in C, U is reachable from V and V is reachable from U. Okay, so
What is it?
he gave an example, right?
What is it?
He told the answer, according to his algo, the answer is 2, but the answer is 1 actually. Any node in this cycle will do. Correct? Okay, so a strongly connected component is a maximal set of vertices C such that for every pair of vertices U and V in C, U is reachable from V and V is reachable from U. So, for example, in this graph, this forms a strongly connected component because for any pair of vertices in this, you can, this is an edge from here to here. For any pair of vertices in this, you can this is a cycle, so you can reach from U to V and from V to U. So this is a strongly connected component. This is also a strongly connected component. Okay, so are you even clear with what a strongly connected component is? So basically, a graph has many strongly connected components. The claim is, so if this is a strongly connected component, just replace this with one huge node. If this is a strongly connected component, replace this with one huge node. Then the first claim is the resultant graph will be a DAG. That is, it won't have any cycles. Why? Assume the contradiction. We'll prove by contradiction. Assume that it does have a cycle. So that is, this graph can be put like this, correct? Each strongly connected component is replaced by one node. So assume that this graph does have a cycle, say something like this. For every node in this component, they are reachable. For any two nodes U and V in this component, U is reachable from V and V is reachable from U. For any node in this component also, it's same. But consider a node in this component and a node in this component. From any node in this component, you can go to the node having this connection and come to this component and have so for any node U in this component, for any node U in this component, you can reach any V in this component. So there is an edge from U to V. There is an indirect path from U to V. If there is a cycle from V also, you can travel like this and like this. So from V to U also there is a indirect path. So there is a path from both U to V and V to U. So you can basically merge these two components into one bigger component, one bigger strongly connected component. The component graph is a DAG. So assume you have a black box which gives the number of strongly connected components, which gives the strongly connected component graph. You can solve this problem because the number of all the nodes with integrity 0 in this strongly connected component graph is going to be the answer. Because since there is no cycle, you can easily prove that from those nodes you can reach every other node because there is no cycle. Correct? So so all that is left to prove is how do you get this DAG from this graph. So the algorithm for strongly connected components goes like this. You are given a graph G and you have to apply strongly connected components for the graph. So first call DFS of G to compute finishing times f of U for each vertex U. This we have already seen how to do. Okay, so then compute G transpose, and then G transpose is a graph in which all edges are reversed. So all the edges in the original graph are just reversed. That is G transpose. So now call DFS in G transpose, but in the main loop of DFS, consider the vertices in order of decreasing finishing time in the first call of DFS. And then output the vertices of each tree in the first forest formed in library as a separate strongly connected component. I'll explain what this is exactly. So first assume you have this graph. Okay. So assume you have this graph. So call DFS to compute finishing time for each vertex U. Okay, I'll take a smaller graph. So call DFS of G to compute finishing times f of U for each vertex U. So does anyone want to play it? I want to. Great. So after you apply the DFS algorithm, this will be the start time comma finish time of all these nodes here. So next compute G dash. So I'll number the nodes 1, 2, 3, 4. Compute G dash. So this is G dash. So in this, call DFS of G dash, but in the main loop of DFS, consider the vertices in order of decreasing f of U. So order of decreasing f of U will be first 1, 2, 3, 4 only. This will be the order of decreasing f of U, correct? For 1 it is highest, for 2 it is second highest, for 3 it is third highest, and for 4 it is fourth highest. So we'll perform DFS in this order. I mean, it's just 1, 2, 3, 4, but yeah, in a general case, perform it in the decreasing order of f of U. call DFS of G dash, but in the main loop of DFS, consider the vertices in order of decreasing f of u. So first